Okay, folks, let's look at the homework 7 key. The very first problem, it's not magnetism. It's highly relevant though, because it has to do with devices. How do you find the capacitance of some pair of surfaces that can have charges on them? How do you find the resistance between those surfaces if there's a medium in there that has some conductivity to it? How do you find the inductance? Well, that's a related question with magnetism and devices, and we haven't gone over it yet, so that'll be kind of off limits. But the method by which you find the resistance or capacitance could be fair game. So the most important thing to review on homework 7, problem 1, is the method. How do you find the resistance between the inner and outer conductor of the coax? You know all these steps you had to do, Laplace's equation, del squared V equals 0, and find the potential V, the voltage, everywhere as your answer. When you do that, you need to know the boundary conditions. So in all these device problems, you start with putting boundary conditions on the two conductors that surround the region where you're going to solve for the potential. Okay, potential, that was kind of last exam. This one, more important to know the general idea of setting up a problem with a device. When you know the boundary values, 0 volts and say 10 volts, you can find the potential. Then you can find the electric field by taking the gradient of the potential, putting a minus sign in front of it. Then get the total current if you're going for resistance using Ohm's law. V equals IR. R is that proportionality constant, V over I. And it's the definition of resistance. Capacitance, similar definition. It's the proportionality between charge on one of the conductors and the voltage difference. Here V is always a voltage difference on the two conductors, resistor, capacitor. So we have to find a connection. The hard part, the stumbling block for a lot of folks working these problems is, do I get to put whatever voltage I want? Yep, you do. You put that voltage, 10 volts, you solve for the current that's drawn, and if you put 10 volts, you should get 10 times the current that you would get if you put 1 volt. It all kind of comes out when you take the ratio. Okay. Hopefully, the voltage that you put will drop out of the solution. You have to go out on a limb a little bit with these problems. So let's look over at the key for this one. See if I can turn that up. It's on Blackboard. It's all worked out. You have to calculate the current density using J equals sigma E conductivity. Okay, we've got E from Laplace's equation kind of indirectly through V, working backwards using an old solution, and it's all perfectly good. Wouldn't necessarily have to do this on the test that's coming up. You have more likely to just explain the steps that you would do. Okay, kind of put them in a sentence. Might be multiple choice, for example. Okay, where do I find the current? What surface do I integrate over? Any surface that all your current has to go through. You could use this outer thing outside the dotted cylinder I picked. You could be a minimalist and pick a smaller cylinder. Doesn't matter. Same amount of current is going to be flowing through. That's how it gets from the inner to the outer. Okay, so we're working all that out in this part of the key. And just pay attention to the big picture here. How am I actually doing this? And I've got another device example where we're finding the capacitance of the same thing. It's the extra credit part of that problem. Okay, C equals Q over V. Now we've got to find the charge. We can get that surface charge density from knowing the electric flux density. All right, so go over that if you're confused about devices. It's problem 1, homework 7.